and also a lot of services in it. So the idea of this one is just to give you an idea of introduce you to the world of coroutines. So I want to understand how many people are kind of using Kotlin already in production, typically. Good. Uh, yeah, so the expectation is not to know Kotlin for this talk, it's just to introduce you to the coroutines. And I can already see people from Python conference and all here. So this is not a very different concept from what you have in Python. Of course, the best part of it, Kotlin is always about the syntax. They have taken the best of syntaxes from all the languages. They don't have anything of its own, but they just steal things from every other language. So most of the time here, we'll be talking about the syntactic sugar and the performance that Coroutines is going to give you. So before jumping into this coroutines directly, let's first talk and get on the same page with respect to concurrency and parallelism. This is a very famous talk. I don't know how many people have seen it. So it's a Gopher conference. This is when it's one of the first Golang talks in 2012, where they talk about how they are do different. So I'm just going to give a very small preview of that. So here, the problem statement is very simple. So we're going to move all the books from a shelf to an incinerator to just burn it, right? And you're going to employ gophers for it. So the gopher's job is to carry books from the shelf and drop it at the incinerator. And you have a couple of bottlenecks here. One is on the loading side of it. So you have to load. You can only load, only one gopher can load books into the cart. And similarly, only one gopher can unload the books from the cart into the incinerator. So there is a bottleneck there. This is how a concurrent solution typically looks like, where you employ 4 gophers because you're rich. So you employ 4 gophers, and one gopher's job is just to keep loading things and pass it on, loads the cart completely. The other gopher's task is to move the cart from the shelf to the incinerator. The third is to unload, and fourth is to return the empty cart back. So here, typically, every gopher is assigned a task to perform, and things happen at the same time, but they are concurrent. Another concurrent solution is this. You have a pile of books. A gopher is asked to take it from one side to half of it. Let's say if most of the time in doing this process, it goes in traveling from one end to other end, this may be a smart move where you ask the gopher to travel half the way because you do the most expensive task halfway down and ask the other gopher to do the rest of the half of the job. So this is also another concurrent solution. Now a parallel solution looks like this. So parallel solution is all about resources. You have more resources, you can do it parallelly. So instead of having one bookshelf, you split it into 2 bookshelves. Instead of having one incinerator, you're going to make it into 2 incinerators. Of course, you can make it 2, 3, 4, whatever it is. And you're going to employ as many gophers as possible to do this job. As you can see here, parallelism is purely about richness. So, and of course, the best solution is going to look like this, where you're getting all your gophers to do the job concurrently. At the same time, you are also good at resources. You're going to just make it parallel. So typically, this is what we all strive at. This is kind of the best solution we have amongst whatever we've shown in the past. Now, talking about this, so what are we thinking about? So here, yes, there is concurrency, parallelism, everything. But the concept is going to be about designing your solution around concurrency. Achieving parallelism is straightforward. Just throw in resources, make sure everyone has its completely independent things to work with, and it will work. Of course, you need to worry about how to combine them eventually, but still it will work because it's relatively easy. Designing concurrent solution is going to be the complex thing. And parallelism is not too different from concurrency again. So concurrency is kind of the basic thing that you need to strive for, and parallelism you can achieve eventually. So concurrency here, yeah, it's the way of solving a problem, and that can be parallelizable in the future. So look for concurrency and things like that. Now, let's go into how we generally do that as part of coding. So let's take a very simple problem statement. So this is going to be an add to list, very simple. This is Kotlin syntax, but I don't think you really need to know Kotlin to understand these things. So yeah, this function is all about adding items to the list. So we are going to do 3 operations here. First is to for this list ID, we're going to just check whether the user is authorized or not. So basically, this function is going to give you back a token. And using that token and with our list ID, you're just going to update a content in the list. And third is, once this operation is successful, you're going to make sure your local copy of the list is maybe marked as synced or marked as updated or something like that. This is a typical problem statement. And as you can see, this is quite straight. No, this is very synchronous. You already see two network calls, one to get the token, one to update the list. And the third is the database call may or may not be expensive, depending on the solutions that we have. This is kind of a very hard problem to parallel technically, unless, I mean, you can parallel for the number of users, but you can really not parallel within the solution because you need, for the step number 2 to happen, you need to have the step number 1 in play, So at the same time, it's, yeah, so you can, if you see the scale-wise, the users-wise, you can use one thread to serve one user, the other thread can serve the other list or other user. So let's start about the solutions, right? The first idea that will come into our mind as a developer, at least for me, whenever people talk about concurrency, threads. Threads are the solution that I used to in Java, every other language I've seen except JavaScript, but still, it's a way we always think about solving a problem using concurrency. So typically, threads aren't cheap. They're expensive. Roughly takes around, let's say, I mean, on average, at least the applications that I've seen, typically it takes around 2 MB of memory for a single thread. We can configure, we can do a lot more stuff, reducing the shared resources, increasing the heap size, stack, everything. But still, they aren't cheap by any means. And for a given hardware, it's going to be a finite number of threads, and it is very, very hardware specific. You want more threads, you need to buy more hardware. You need to get a better RAM, better hardware processing, and stuff. From a developer point of view, it's definitely not easy to work with. I mean, most of the time, what I do is like I write a code which is non-threaded or very synchronous, and then just believe in the syntax of thread and just write the code for the threading. It is kind of hard to debug. It's kind of hard to write a test around it. You got to mark a lot of things, and it's kind of very hard to make sure the errors are propagated in the right place. If there's a sequence of threads, if one thread gets cancelled, what's going to happen for the remaining threads? Those kind of questions are very mystery. We just sit back and wait on the production, what's happening, and then let's see, kind of thing. The second option is callbacks. Coming from the Node.js, I've written a lot of Node.js code. This was like a wow factor when I saw this. Oh, this is the thing that we're going to solve everything with. It looks cool. If you have already done a lot of callback-based programming, this looks pretty easy thing. But it's not natural, actually. So this is not how a human mind reads code. We don't like top-down modular programming, but our mind always trying to read the code top to bottom. But this is composition. So you have to see, okay, what's the first line? Okay, authorize is going to happen. Okay, and then there is a update list that is composed, and then there is an update DB that is composed. It's very hard to read, and again, error handling and propagations of errors are not going to be easy, especially, and if you want to add loops, more pains. We don't know how things are going to work. We just believe on a few things and keep going. Other is the RxJava futures, promises, solutions. They are trying to solve the readability of callbacks by maybe like having a very nice, see this? Okay, by having exception handlings made easy, and you have a lot of future combinators, they call it as. If you want to do two things sequentially and then the third thing parallelly, it's all doable. But you need to know a completely different world of things, which is called future combinators, futures, and everything. It's not a library. It's specific to every language. Java has its own tons of future combinators, and so is C#, and so is Python. So that's a different world that we need to know. And if you are okay, we can deep dive into it. But again, that is one thing that we need to do. So at least for me, this coroutines is a new way of solving these for this threading things. So before questioning a lot of things, let's quickly see how a coroutine code will look like for the similar problem. this is exactly what a synchronous code looked like, except that we added a suspend function in the top. And Kotlin is developed by JetBrains. And so typically Kotlin developers use IntelliJ. And if you are using IntelliJ for Kotlin, you're going to have two nice symbols next to some functions, indicating that these functions are also suspend functions. You don't need to worry about what suspense functions and everything. I'll try to cover them. But syntactically, this is the best that you can achieve. It's top-down and a very synchronous style of programming. And so using loops and everything, it's going to be pretty straightforward. I mean, you don't need to worry about asynchronicity here. It's just like writing a normal synchronous program, just adding a suspend keyword at the top. And again, the best part of Kotlin for me is it can run in both JVM as well as it can transpile to a JavaScript. The same piece of code, like Kotlin, like coroutines that we see here, can be transpiled. There are no threads in JavaScript, right? But still, coroutines will work. And interestingly, JVM also doesn't support by default something like a coroutine context, like what you have in Python. But still, Kotlin supports coroutines because coroutines is just a gimmick in the Kotlin that actually converts all these code into callback methods. So there's no JVM level magic. All the magic just stops in the compilation of your code. Once you see your byte class, you'll be like, oh, is this Kotlin or is this coroutine? It'll be as simple. It will be compiled. All the magic happens right there, and nothing happens beyond. There's no JVM tweaking or there's nothing on that front. So, which means if you make your compilation or transpilation intelligent, you can run it on different environment, which is what they do for JavaScript. They provide a transpiling ability on the Kotlin that can be converted to JavaScript. Again, it uses a different semantics and things, but it runs on a browser. So now let's try to get what our coroutines are. Oh, this is how a Wikipedia definition looks like. Let's not go deep into it. But the lightweight, in simple words, it's actually lightweight threads. But I like simpler than this. I mean, lightweight threads, there are a lot of things. So I was just Googling for, how can I explain it further? So I saw this article about coroutines. This is not specific to Kotlin again. This is purely about coroutines. So how you can talk to a 10-year-old what a coroutine is. I don't know why you need to talk about coroutines to a 10-year-old, but still, let's say. Let's say for the 10-year-old, let's say you start watching a cartoon, but it's intro, So the kid doesn't like the intro, so it doesn't want to wait for the intro to get over. So they skips intro and then decided to play online and opens up a multiplayer game and asks friends to join. Friends say, hey, no, just give us some time, we'll join. Again, there is a waiting required. Kid doesn't like waiting. So starts moving into do the homework. Now, picking up the homework, realized now it's not doable right now because it needs some more constraints or some more resources need to be purchased. Okay, so come back to the cartoon. Now the intro is over. So now they can enjoy the cartoon finally. And now we have commercials in the cartoon. So, and then they went back to the online games and the friends were back. So they start playing. So what happens here? So typically it's one person doing only one job at any point of time. The kid is not doing two things in two different hands. It's just one thing. But the best part is the kid knows where to stop and when to come back to the same point of time. So this is all about coroutines. It runs in a single thread, typically. It has a start, it has a stop, it has pause, everything. It knows exactly when to come back to the same point to resume the action from that particular instant. So this means that imagine you have a multi-threaded application. In one thread, technically here I'm doing 3 different tasks. Of course, I can scale it to 5 different tasks or 10 different tasks depending on my wait times and depending on my things. What if I have a multi-threaded application? I'm just increasing my ability to scale on a 2-dimensional angle within the threads and across the threads. So we also saw Kotlin, these coroutines are nothing but lightweight threads. what does it mean actually? So this is sample code. I actually thought of doing a demo, but my machine is super powerful, so this code doesn't still fail. Maybe not this, but this is 1 million. I'm trying to run print a dot for 1 million times with a weight of 1,000 milliseconds. So this is again a Kotlin syntax, works perfectly fine. But what happens in a normal machines are typically get an out-of-memory exception. What happens behind the scenes is, so thread actually uses heaps. Like they keep stacking things. They build their own context. They build everything of their own. They keep pushing that into the stack. And there is a limit, right? Your machines are not like, of course, people have supercomputers, but still, it can't sustain after some point of time. The same code with coroutines will run seamlessly. Because here, you don't use the same amount of resources that the previous code was using. We don't spin off so many threads, even if it's waiting. We don't simulate so many threads. We try to do context switching. If there is a wait, we try to pick up and go for the next job instead of starting a new own resource cycle of its own. So by that means the resource consumption is pretty limited, and hence so it will run perfectly fine on a machine. Relatively to whatever we saw with the thread. So there are two magic words here. Again, I'm saying like you don't need to really go deep into the syntax here. You can definitely read those things in the documentation. But these magic words, these magic blocks are going to be explained in the next thing. So one thing that we need to work with coroutines is, they call it as coroutines builders. Again, this is very Kotlin specific. You don't have it in Python, I hope. I'm not sure. This is very Kotlin specific. It says coroutine builders. So we saw a function with suspend in it. There is only one constraint with it. You cannot call a suspend function from a non-suspend function. You cannot call a suspend function from a very normal written function. But what you can do is, instead you can use one of the coroutine builders that come with language. Kotlin has got a lot of coroutine builders. On this thing, we're going to just see two of them, which most commonly been used. At least I have seen it. At least three. So both the words that we highlighted before, run blocking and launch, both of them are the coroutine builders that comes with Kotlin. So what do they do? This main function, this is a normal function. This main function is typically a non-suspend function. So if I try to call a delay, which is actually a suspend function here, which is actually a coroutine, delay is also coming from the coroutine, like Kotlin package itself. So this is a built-in function. It's same as thread.sleep. So this is a waiting function. So this function cannot be called directly in the main. So what you have to do is you have to launch something. What this launch technically does is it actually issues a dedicated thread to run your Kotlin or run your suspend functions within that scope. So this code is actually running in the global scope. That's very default. That's very common and very easy to use. You want more customization, you can build your own context and say, run within these contexts. It's all doable. And the other thing that we see here is run blocking. This is going to be, somewhere you need to block it. Like, you cannot just keep everything unblocking stuff. So somewhere you need to print a result. So especially whenever you want to close your application or something, like you need to have a blocking. So this is your main thread kind of thing. If you're coming from Node.js, like it's your event loop, technically. So where you're running everything inside your blocking thread, right? And then the blocking thread will spin off other context and things. So there is a main thread that has to run. So this run blocking is going to issue this global context, and this launch is going to give you context within it. So this kind of builder is typically used whenever you have actions like, do something but never come back. We don't really care about the return values. So in this case, it's a print. We don't really care about the print's return, right? Like we just want the print to do some work. The other option is to use async await. This is a very common paradigm in most of the languages I've worked with. So Async await, there's no difference in what it does in the other languages. So async is going to tell that some block of code is async. And if you call an await on that block of code, then you actually make your code typically waiting. So in this example, I'm having a function which is called load image. Load image itself is a suspend function because it makes a network call to load something. That suspend function cannot be called in the main directly. So we have to use a builder. And the builder here in this case is async for me because I really need the function's return value and to do some operations post that. If I had used launch here, yes, it works, but I never get back the result. So I need a result here. So I say, okay, async, do this async, and comes back with a await. Of course, this code doesn't make much of sense because you're doing only one operation inside async, but typically you can make multiple operations inside async because then you can actually chain multiple suspend functions inside async because async is a builder. Inside that, you can keep stacking in all your suspend functions. In this scenario, I'm just showing you only one example of suspend function. So far, all the examples that we saw with Kotlins are typically with I/O. Like we said, oh, there's a network call, it's gonna wait. So let's put a Kotlin suspend there. And there's a database call, oh, it might wait. So let's put another suspend there. But actually, Kotlins or Coroutines is not just for I/O only. Like you can do a lot more things. I like this example very much. A very simple Fibonacci thing. So yield is a coroutine, again, from very much stolen from Python thing, but this is Kotlin. So here, build sequence is one of the builder, coroutine builder, because yield is a suspend function. So yield cannot be called inside a non-suspend function. So you need to use it within a builder. So build sequence is a builder. So what is this piece of code is going to do is, it's not going to give you like a million Fibonacci or thousands of Fibonacci numbers. It's not going to compute you 1,000 Fibonacci upfront, but it's going to do nothing upfront unless you start calling it. So you create an iterator, and on the iterator, you're going to just keep calling next. For each and every next, there is a computation that's going to happen. And this is no I/O, but this is coroutines. Because we all know that coroutines concept is this. It knows where to start. It knows the stop location. It can come back to the same point, and it can resume. So this exactly happens in the Fibonacci. If you call this next 1,000 times, you can compute 1,000 Fibonacci. You call it 2 times, you're done with only 2 times. So your computation effort that goes in here is pretty much a lazy sequence, but here it's a lazy dynamic sequence. The values are dynamic, so you can keep computing. You can apply the same concept in a lot of other places where you have a computational, where you have a very expensive computation. You can use such things where you don't need to pre-compute everything, but you just wait based on the demand, you can compute. So one other topic I really liked about coroutines is exception handlings. So typically, we have exception handling in the cases where you ask thread something to stop. If thread gets canceled, what's going to happen with the rest of the things? I don't know. I need to just wait and try it out and see what's going to happen. Thread was offering something called stop. If you are in Java world, like it used to have something called thread.stop. It's actually deprecated. Currently, it does nothing. But the syntax do exist. There are a lot of problems with this. It's not just stopping a single thread. The biggest question is what happens to the process that was pinned by this parent thread? Can we just go ahead and kill everything? And what happens to the process that the child starts? So it has a serious implication. So this is the problem behind canceling a thread. So they felt it was a very cool idea just to open this API to stop a thread, but realized it's actually not as easy as they thought because they have a lot of implications behind it. So they had to take back. Kotlin do have, on the coroutines, they have cancellations. The same example, like similar examples at least. So we have a repeat, we are repeating the statement for every 500 milliseconds. We just keep printing it for 1,000 times. Whenever you feel like canceling it, you just call cancel, and you say join. Join is going to just make sure it comes onto the main thread, so your function is back onto one thread. So we have, as I said, it also supports cooperative cancellations. What does cooperative cancellation means? It means that it makes sure its children are well communicated. That, hey, I've been cancelled. Now it's up to you to take care of yourself. That's what typically Kotlin coroutines cancellation does. It doesn't say kill everyone. It doesn't do that. So it just says I'm cancelled. It passes the signal to the remaining of the coroutines. So in this case, and all the built-in suspend functions of Kotlin supports cancellation by default. Like it knows to cancel itself, and it will pass on the message to the further children. So in this case, launch, if you cancel it, let's say there is a 50,000 milliseconds delay of this thread, and if you call cancel on this one, it's not going to call the last print statement, and it's going to just stop right there. It's not going to wait for the 50,000 milliseconds and then kills. Even if it starts this delay is another suspend function, right? It's technically another coroutine. So the launch, which is the first coroutine, it's going to just help passing this information to the delay, and the delay is going to just wait. Delay's way of handling cancellation is just to stop working. So that doesn't mean all the coroutines has cancellation inbuilt, right? But all the Kotlin X coroutines that comes in the package of Kotlin are cancelable. Basically, you have to read the documentation of what they are going to do at the time of cancellation, but they actually are cancelable. And again, they also pass on the information to the child coroutines about the cancellations. But any custom suspend functions that you write are not cancelable or doesn't know how to handle cancellation by default. So it's your responsibility when you write a suspend function, it's your responsibility to take care of these cancellations. You can just say, if I get a cancel signal, or it's just nothing but a variable, it's just a Boolean, it say active or not, and then if it's active, keep doing it. If it's not active, do something, get out of the function. So you have to do that. And also you have an option to make your suspend function non-cancelable. So there may be instances where you don't want someone to cancel your operation. And cancel actually here works very much like a try catch, because it actually throws an exception called cancel exception. So you can also do finally there. So even if your function gets canceled, so typically most of the cancellation code will be like this. You say try catch, and then catch this cancel exception, and do some finally. Because you need to wrap up things. You don't want to just leak stuff as it is. So you do that as part of cancellation on your custom code usually. Yeah, so as I mentioned before, like we're working on an Android project there, and that uses Kotlin, and we started using Coroutines a lot. It's typically the best use case I can think of, because these apps will be running inside the mobile phones. They're not as powerful as your laptops or production service that you run in cloud. These are mobile phones with typically relatively less power than production service. So running threads, and I don't know how many of you know this, but in Android, almost every operation is banned on the main thread. Main thread is responsibility is just to make sure the UI is rendered. If you want to make a network call, you have to spin off a thread. You want to make a database call, you need to go into a different thread. You cannot do anything on the main thread. And literally on the runtime, Android doesn't allow you to do those things. So threading is like a very core principle inside an Android applications. And as I said before, threads are expensive. So it's very common to see out-of-memory exceptions, out-of-memory errors when you use threads, because everything happens in a different threads. And there is one UI thread that controls only the UI. So now how this coroutines are going to be super helpful is we can currently, as of today, we can definitely use coroutines in the Android, and we can push it to production. It works because eventually Kotlin just compiles everything into some class files and works. But coming up in Android, in the coming versions, it's official that Android Q will support Kotlin coroutines as a first-class objects or first-class controls, they call it as. So what that means is Android has got its own pieces of components. They say use this to make a network. Use this library called retrofit to make network calls. You can use room to make your database calls. And live data is an observable object where you can do this. Now, all these things will start supporting coroutines by default. I can show you an example of what the impact will look like. So this is exactly a piece of code you write in Android. It's just a similar thing. You query for a nodes from the database. You upload the nodes to your service, and you mark this information as synced in the database, and returns back success. This DB call, let's say if it's coming from room, then room supports suspend function by default. So which means this query new nodes is going to be a suspend function of its own. And this upload nodes is another suspend function because retrofit also supports suspend functions. And now mark as synced is another database call, which can also be a suspend function, and because room supports it. And this worker is a typical work manager. It's there in Android, which also supports. It's kind of a builder, the coroutine builder. So typically you can run all these things within that block of code. The best part now is if I say this worker.cancel, I don't need to write a single piece of code to make sure my exception handlings are done, because this worker thread will announce the same to the room, say this operation is canceled, just stop wherever you are. And room knows how to handle this cancellation request. Same with a retrofit. The network call can be stopped or can be canceled if the parent is canceled. It doesn't need to throw any exceptions on the runtime, but it's all well gracefully handled within the piece of code without rewriting a single piece of code. So for me, this is a big deal. So yeah. Actually, that's all I had for this talk. Happy to take questions. I'll be here. And yeah, and happy trying out coroutines. You can look into coroutines. Kotlin, there is a live page. You can go and try it out. It's super easy. You don't need to install anything on your machine. You just need a browser. Go into the Kotlin documentation. You can try out your code automatically there. And have fun. Any questions?